just we can start asking questions. I don't know how this is, how much this setting of on-site online lectures is going to last. So whether this is the last on-site lecture we're going to have, or we're going to have more of those, I have no idea. So no matter that, we have a clear structure organization. So if we are not going to be able to do physical classes anymore, which is not sure, but not unlikely, we're going to move the Q&A to Zoom. So as most of you have experience where you were not physically here, and we're going to continue today with that. Okay. Otherwise, we're going to keep meeting on Monday at 2 p.m. Even today is different because yesterday was closed, but otherwise we'll keep with the structure. Yes, I don't have any other announcement, so we can start with questions and hopefully answers. So I don't remember last time at what point we arrived here, because there were a little bit desynchronization between you people on Zoom. I think we stopped at lecture 6. So is there any question about lecture 6 or previous ones?
Can I ask?
Yes.
For the part where there are conservative systems,
yes,
and then we have the equation of motion.
Yes.
We have equation of motion. So we just get the equation wherein the motion is constant.
I'm trying to. Okay, so what is the question? So we have the conservation of motion. So we have an equation where we have a quantity which is conserved over time. Is that the question you are asking? I think you're asking?
Yeah. So
yes. Okay.
So we just get the equation wherein at that equation, this value is conserved.
Yeah. Yes. I don't understand if you are repeating what I said. Do you want a feedback if you said it correctly, or it's a question? So I can. So we have an equation like x equal to f of x. Okay. And we have a quantity e of x, which we say is conserved if d is p, which is equal to the sum over I of d xi is equal to 0. Okay. And when I was talking about conservative system, I said, well, of course, there is an obvious choice, which is a equal to e of x equal to 37, right? If I choose a function which is actually constant, it's obvious that it doesn't change over time, right? It doesn't change over time because this is equal to 0, right? So if you choose a function such that all of these partial derivatives are equal to 0, equivalently, a function that does not depend on x, this is obviously 0, right? That is not a meaningful choice, right? So we want functions that are actually function of the variables that change with these variables. And then perhaps what you're asking is when I say that has to be non-constant in any open subset, something like that. Yes. So is this clear? Okay. Good. This is most of what I wanted to say. So the point is, if you choose a function which is constant, then of course this is trivially equal to 0, but that's not interesting. Okay. So when we stated the theorem about closed orbits in 2 dimension conserved quantity, what we said is that if it exists a function such that is not constant in any open subset, with these properties, that then we have closed orbits. what does it mean that is not constant in any open subset is that if you take any open subset of R2, the function has not to be constant in that open subset. Now, in practice, if you have a function that is analytic, so all the derivatives of the function exist, then this condition is equivalent to say that the function is not constant. Okay? So basically what you're saying is, I want a function that depends on the variable, which is smooth, perhaps, so this derivative exists, but depends on the variable. So if I move in an arbitrary direction, or I take a bubble, you take any point, and you take a bubble around this point, the function has not to be constant in that bubble. That is what this means. Okay. Otherwise, if you say something which is constant in a bubble, then it's obvious that within that bubble is going to be conserved, right, by definition, because the function does not depend on the variables. Okay. Behind mask, I can pretend you are all saying yes. Everything is great. Good. Yes.
At the lecture, at the beginning of linear systems,
okay.
When you were defining the transpose, you were multiplying. I couldn't understand when you write it by components to sigma vi alpha vi beta is equal to delta alpha beta. I couldn't understand this. How you write this? Why the notation became the same? Here. Just the notation.
Okay.
Both of them.
So what I said is that if you have a symmetric matrix, you have a matrix which is orthogonal. Okay. And I say, I take this matrix here, and I say, well, I call these, let's say, I call these columns, I call this column here a vector V alpha, okay? And therefore, if I take the component I, this is like V alpha I, okay? This is not perhaps, this is one possible notation. I just chose it because it becomes clear what I consider the eigenvectors and the, right? And then what I said is this condition here, if you use this notation here to indicate the matrix, can be rewritten as sum over I, Vi alpha, Vi beta.
My problem is that because why both of them becomes I.
Because imagine I have V transpose, right? So when I multiply these two, what I do is that I multiply a row by a column, right? Now, a row here of V transposed, this is like the vector V, if you want, transposed beta, right? So I always multiply a vector here with a vector here, but this is equivalent to say, since this is the transposed, this matrix is the transpose of that, it's equivalent to say that I take two columns and I multiply them, right? When I do the matrix multiplication, I multiply the row of this matrix times the column of this matrix. Okay,
yeah.
But this is the transpose, so it's equivalent to say that I do this. Okay.
I have another question about linear systems.
Yes.
It's when we have the matrix that is not symmetric, I have to find the eigenvalues and then find the maximum of them, right?
Of the?
Of the eigenvalue of the matrix. So
Yes.
to find that if it's positive, we are find that the system is going to be in equilibrium. Or
Yes.
not.
Yes.
But when it's the part the eigenvalue is imaginary, that is different from zero. I think that I can.
Yes, the condition. Okay, so the condition is that the maximum of the real part of the eigenvalues.
It doesn't matter about the imaginary part.
For the stability, no, right?
So I can ignore the imaginary.
Yes. So if you want to check whether the system is stable or not, the imaginary part doesn't matter for the stability. Right? Only the real part. And the reason is that you can show that the for large times the system behaves like e to the minus to the real part of the eigenvalue of the maximum one, t times the cosine of the imaginary part of lambda t plus of x. Okay? So the imaginary part just contributes to oscillations, and the real part is what contributes to the dampening towards zero. So if you look at the trajectories, they look something like this, right? So you start here, and you have.
Yeah, and I have another question, because this maximum, it will tell us about the stability, but you say in the video that if even just one of the eigenvalues is positive, the real part, even the system goes to minus infinity or minus.
Yes.
But even if one of them.
That means that it exists. So if you have a large dimensional system, now imagine that you are in 7 dimensions. That means, and you have one eigenvalues which is positive. That means that there is one direction where if you move in that direction, you're going to go away.
Okay.
So that means that if you move exactly in a direction that is orthogonal to that direction, you're going to go back to zero. Okay. We can do the exercise in 2 dimensions.
The only condition that matters, I think, that is the maximum, right?
Yes. So the point is that suppose that you have 2 directions, and this 2 direction corresponds to the eigenvectors, and you have one direction with an eigenvalue which is positive, right? And the other one which is negative. You have something like this, right? Okay. The point is, if you move exactly in this direction, you're going to go back to zero. If you move anywhere that has a non-zero projection on this direction which is diverging, well, you're going to do something like this, and then you're going to go to infinity. So the point is that even if you are in 7 dimensions and you have only one direction which is unstable, unless you move precisely orthogonal to that, you are safe. If you have any small projection on that direction, you are going to flow there and then go to infinity. Okay?
Yeah.
You like this? Yeah. I have to move because I'm freezing. I mean, I'm not freezing. Huh? Yeah, but I mean, the reason I'm doing that is because I'm talking loudly, and I mean, so I don't want to accumulate too much aerosol for you. Good.
Excuse me, the maximum over beta of lambda index beta means that we have a number of lambda beta, and we are choosing the maximum one.
You're choosing the one with the maximum real part. Okay, that is what determines stability. Okay. Okay. Good. So, yes.
I don't remember if it is on text 6 or 5, but you usually introduce the matrix that describe the systems to be symmetric. Is it only for the sake of easy calculus, or there are other?
In which part?
It's like, so for the part when you introduce the function L, for instance.
The for the competitive Volterra existence of a Lyapunov function. No, it's not just for the sake of simplicity. Is that if the matrix is not symmetric, that function is not a Lyapunov function. Okay. So you can, let's say this. You can. I can show you if you want, but the point is that if you define like that the Lyapunov function, you can, and you write the derivative over time of the Lyapunov function. If you assume that the matrix is not symmetric, you can show that that matrix is not, that function is not a Lyapunov function. And so the point is that if you write dl dt, this function here is lower or equal than 0 in general, only if aij is equal to aji. I should technically write if. I mean, there are other conditions, sort of a little bit more general conditions where the matrix is not symmetric, but this is still the Lyapunov function. But if the matrix is symmetric, it's clear to prove that. If it's not symmetric, there are cases where that is not the case. And one simple way to check that is that the Lyapunov function is defined as something ni, aij, and j. Okay. So here you are multiplying a matrix times these two variable vectors here, which are, of course, this sum here is symmetric under the exchange of I and j, right? Because you are summing over all the variables. So that means that the non-symmetric, the anti-symmetric part of A doesn't matter to this, doesn't count to this sum. Okay? So that the value of the Lyapunov function depends only on the symmetric part of this. So yeah, so if it is not symmetric, the situation is more complicated. That's the answer.
So, because when you see symmetric matrix, you are just saying that the species A contribute to the species 2 as the species
That's
2
right.
contribute to
Yes.
the species A. So it just like, it sounds easy.
Yes.
Yeah.
That's why. Yes. It's easy. Yes. It's easier to do easy things.
For us, I mean, in real life calculation, can you, for instance, like suppose that the interaction are symmetrics and just work?
It depends on the interaction, right? So, for instance, I showed you in lecture number something, I think it was 8. I showed you how a Lotka-Volterra equation can emerge from a consumer resource model, and the competition is basically something that is the overlap of resource preference, right? So let's say that we have like there are 4 species that compete for the same resources, okay? And you model explicitly the dynamics of species and resources. Then you do the separation of timescales. What you get under center condition that I'll explain in that lecture is that the dynamics of the consumers can be described by Lotka-Volterra, where the interaction matrix A, Ij, can be written as something like the sum over some alpha of Ci alpha, Cj alpha, okay? Where Ci alpha is how much of resource alpha does species I consume, right? So this is like the overlap of preferences, right? So I like to eat pasta and pizza, and some of you like pasta and pizza, some others like more rice, others like more beans, I don't know. And depending on how much is the overlap of our preferences, then contributes to the competition. Now, note that this is by definition symmetric, right? And therefore, in that case, for instance, it's natural to have a symmetric matrix. Does a real life ecosystem can be described by symmetric? It depends, right? So, I mean, the point is that it's, it's how many details you have to include to understand what's at the phenomenon in place. Right? So, I think this is a very good null scenario or conceptual scenario, which makes sense in many cases. Right? Yes.
Can we say that some systems are more stable than others, right?
I mean, you can say that.
Yeah, it's that I want to. It's about the homework because I want to do like.
So yes. So let's say stability is a 1 or 0 property, right? So either you are stable or you are not stable, and you are stable if you. I mean, a system. Sorry, I use you as an in-person, but a system is stable if the real part of the eigenvalues of all the eigenvalues is negative. Yeah. It's unstable if at least 1, right? So it's a 1, 0 problem.
I asked because sometimes some eigenvalues are bigger than others.
Yes. So okay. So if
because it's like sometimes I will find that some systems are more stable.
Well, I mean, the point is, I don't like saying more stable or less stable because stable it's really a 1 or 0 property, right? What you can say is, if you look at this expression here, the value here tells you how rapidly you move away or toward the equilibrium, okay? So this term here tells you how much rapidly you change after perturbation. If this is negative, how how fast you go back to the previous condition. If you are unstable, how fast you move away. So sometimes this is referred to resilience. Right? If this is negative, right? You are resilient if you go back to the previous state fast enough. So if this larger value is very negative, it means that you go very fast to the previous state. If it is close to 0, it means that it takes some time. But I will not, I mean, this is in a way just how you use words, so it's not super important. But I will not say more stable, less stable. I mean, stability, it's really. On the other hand, just to give you a hint on that, I mean, you can say something is more likely to be stable or less likely to be stable. Right? Good.
Excuse me, again about my first question.
Yes.
I noticed that we had all in that multiplication, we had all I and j, but those that I and j were different, all of them became 0. Because of that, we removed them from this.
Yes, so you can do two things. I mean, one nice properties of this matrix is that this quantity here is 1 if the two indices are 0, but it's also true for the transpose, right? So this is, if you take the j alpha, alpha, this is delta j.
I mean, this expression just is speaking about the diagonal components, yeah?
No, it's speaking about all of them, because if I is different from j, then it's 0.
Yeah.
So this expression here, it's equivalent to say that this matrix product is equal to a diagonal matrix, to the identity matrix. Right? So if I say that a matrix product is equal to the identity matrix, I'm talking about all the entries of the matrix.
Yeah.
It's the identity, so all the zeros and all the ones.
If we are talking about all the components, we have to both have I and j different and alpha and beta different.
Yes, so the point is that if you do this sum, either for I and j different or for alpha and beta different, but not both. I tell you.
My point is both of them at the same time be different.
What you mean, but then you are saying, what is this number here?
Yeah. I'm saying that when we are writing that both of them are I or both of them are alpha, it means that we removed all other components and we are talking about just the diagonal.
No, it means that you are taking this row vector here and multiplying by this column vector, or vice versa, you take this column vector and multiply by this row vector. This is what you're saying. Okay? But you take all the columns multiplied by all the rows, or all the rows multiplied by all the columns. Yes. Yes.
Can I ask, for some systems that exhibit hysteresis, so like the region where you can see the hysteresis is also dependent on the degree of stability?
It's a good question. I have to think. I mean, I would say not necessarily, in the sense that, well, I mean, it's not easy to, so you are talking about two different properties, right? So the degree of stability, well, okay. So you want to know whether this, how big is this region, is related to
The degree of stability.
which means
So, no, so I was, my mind is in a like electronics system. So sometimes if like the REP is longer, I mean, if the decay is longer, the hysteresis is bigger.
I think, I mean, this is, I think that then in general, there is not need to, so what you're asking is something like, does the, so if you look at these, in this region here, you have like a potential, right? Okay. So somehow you want to relate how big is this region here, okay, to the degree of stability, to how fast you go back to equilibrium after a perturbation, which is related to the curvature here. Okay. This is in practice what you're asking about, and you're asking, there is a relation between this and that. Right? Now, in practice, what you do is that you change one parameter and you move in this phase space. And so basically, if you are here, you have something like this. If you're here, you have something like this. Okay. So informally, typically, sometimes, often, I expect that there might be a connection between how big is this and how much it takes to transform this into that. But that is not something that has to be necessarily the case. Right? What I mean is that you imagine that you take a family of functions where you can go from this to that, let's say a quartic potential, you probably find the property you are talking about. Okay? You find that if you have something that this is here is more narrow, okay, then probably this is also more narrow. Something like that. But I mean, they are two different. My point of this picture is that they are two different properties, right? In general, you can have something very long and also have something here which is very, very narrow, right? So it's very, very stable, and vice versa. So I don't think it's like a necessity. Yes. Okay.
I am freezing. Can you please?
Ah, freezing. We can close it for a while. I don't want you. Let's close it for a while. Okay. Good. Let's close it for until you are freeze. When you reach 36 degrees, then. Okay. Good. Sorry. We can put something on fire if you want. Great. So, other questions? Let's try to go on with order because okay, no, we have time. Questions on 4, linear algebra. We already answered some. Other question on that. Other question on that 3, other question on that 2, other question on 1. So, question on 5, which I don't remember what it was.
Bifurcation.
No.
Oh, and so I have. Okay.
No, if you close the door, we're gonna. No, let's leave at least the door. Yeah. Because I mean, the point is that the reason why I'm doing that is that I have a mask, but since I'm talking a lot, I'm generating a lot of things.
Yes.
Right? Now and since you are many, I don't want you to risk anything. I mean, okay.
With that would be assuming that you're fun.
Yeah, I mean, which is something that likely I'm not, but I mean, I don't have the certainty, right? So
No.
I think it's better to. I mean, if you look at the prevalence in the population, it's probably about 2% of the probability, which is small, but it's not 0.
Yeah.
So can we leave this open?
Yeah.
Okay.
Can I come get my jacket?
Huh?
You can open the window.
Yes, you can go.
It's in my document.
Yeah. I mean, we can. We don't need to keep it always open, but we can go. Good. 5. You had a question.
It's good. It's about bifurcations, but I prefer to write it.
Okay.
You then.
Okay. Okay.
About bifurcations.
Okay.
So in So initially we only did up to chapter 7, which was one dimension.
Mhm.
And now are we going to start chapter 8 in Stoke? Or are we not going to?
Well, I sort of, there is a video on that, the one on, so we are not going to go deeper than what I said, okay?
Okay, because I was a little confused that I was going to stay there. Or...
No, we are going to move fast.
Oh, I have an answer.
Okay,
And then homework,
okay.
what is the meaning about say that the matrix II is equal to -1 and the diagonal of diagonal?
So
What is the meaning of that?
meaning in terms psychological or meaning in
Yeah,
terms of...
why you say it's
Who was laughing? Why you were laughing?
It's a compliment.
Huh?
It's a compliment.
Okay.
Okay, so you were saying why AII is equal to -1, AIJ, I don't know.
No, it's random.
Yeah, AIJ is random.
Yeah, but why it's the -1 in the of
Why did they put -1
Yeah,
and not, you will discover. I mean, in some sense, if I tell you why I put -1, if I tell you why I put -1, I mean, let's say, try to solve the problem and you are gonna understand the posteriori why I put
I
-1.
did, but well, now complete.
Well, I mean, let's say, regarding the exercise, I don't want. I mean, I'll be a little bit hesitant to answer to the questions because I mean, if there is something that is unclear that which happens 99% of the time. So, but if there is something that it's not clear for the exercise, I'm happy to answer. If it's something that can give you some sort of bias toward the solution, not because I want to, it's just because, I mean, I think it's better that you explore. So, for instance, this question, if you ask, why the hell did I choose -1 and not -37, which is my favorite number before, try.
Okay. Because I think that you want that we do a graph about.
I'll try not to do any special expression, which is easier with the mask.
Yeah. Is that I was trying to write a program and I think that I have to plot the values versus the standard deviation and see something from it.
Yes.
Okay.
Yes.
Well,
yes.
Is the size of the matrix also, I mean, random?
No.
No.
Why
The
did
matrix is the number of particles of species.
Yeah.
No, I meant, why did you?
Why did they put, well, I mean,
It's random.
yes. This is a hint, right? Yes. I mean, the point is, all these I think is because I didn't tell you. So all these exercises are also meant to, I mean, they are explicitly not the standard exercise of a textbook, right? I don't want to give you the exercise where you basically take what I did in class and you repeat it like the same with a comma, which is different, and then you have to do like 3 pages long of calculations. So another important point, all these exercises, or most of these exercises, should not involve like huge complicated calculations, right? So sometimes if you get stuck in some calculation, it's more likely that there is a way to do that without a calculation.
Yes.
Okay. But the point is that sometimes the exercises are also formulated in a way which is explicitly on purpose not clear. In the sense, I don't want you to say, oh, tell me the number of species that are left in this. It's more like explore something with this, right? So it's more like ask yourself a question which is meaningful, and then answer correctly, right? So,
For the homework, should the answers have like more comments or conclusion on each part, or we just answer the questions and move on?
Well, I mean, it depends on what the question asks.
It depends on the question.
If it's, there are some questions that ask like, is the phenomenology the same, right? Or I mean, find a functional response which has the same phenomenology. Then you have to tell me what is the class of functions that do that. Like the last exercise, I think, is one of the most open, which basically it's come up with some equations, study them, and tell me something interesting. Then it's open. No? Okay. Yes.
In the homework, you ask us to find the case.
Find?
You ask us to find the case.
Mm-hmm.
And the relation which you give to us, we was start with the value of delta t. You don't know how to find delta t from the system.
Which exercise?
It's number, the delta T.
Exercise
B.
B.
Exercise B.
Okay. Yes.
Delta T,
Yes.
D.
Okay. So
We was able to find the
D.
B.
Okay.
D. Like,
Delta
yes.
difference.
Mm-hmm. What's the question? Sorry.
we was able to find the period, but to find delta t, we don't know how to do it.
To find the phase. Yes, the phase.
Delta t.
Yes. I know. I mean, it's not. Yes. You have 2 weeks
I
more.
wanna ask.
You have 17 days more.
What?
You have 17. I mean, that exercise. It's actually. I mean, let me say this. When I was saying, oh, you're gonna find yourself doing a lot of calculation and it's much easier. This is one of the exercises where this applies.
Yeah.
Okay. So it's, I mean, yeah. Other questions? Let's keep moving randomly between exercise. Go ahead.
From 6. 6 also.
6.
From 6. It is about the Lyapunov equations. Yeah, if I remember it correctly, we said that the existence of a Lyapunov equation corresponding to the system is one way to prove the stability of the fixed points.
Yes.
Is there some kind of trick to formulate this function? Because it doesn't always exist.
Okay. So your question is, if we can build a Lyapunov function, we are great. We know everything. We can basically. Okay. And the question is, like now you give me a dynamical system. Is there a way to build it?
Yeah, it's
No.
not a trick.
No.
Yeah.
So there is no method to, let's say, that you can apply in general to build a Lyapunov function. Because the two reasons why is that you don't know if a Lyapunov function exists, and you have many systems where it doesn't.
Yeah.
Right?
So for the one that we discussed in class, do you know how they come up with this?
I mean, yeah, that's the other part of the answer. So how do you come up? It's like a mix of inspiration and so it's, I mean, it's not that people do that as a research. I mean, it's something that you somehow go by trial and error. Okay. So for instance, I basically showed you two Lyapunov functions, this one and the conserved quantity in the Lotka-Volterra predator-prey is the Lyapunov function if you add a carrying capacity. Okay. So, for instance, in this case, you see that the Lotka-Volterra, it's like something plus a linear function. So you say, well, in Lyapunov function I have derivatives. Let's try a quadratic function, and it works. But there is no way to construct it. The other important point is that there is no. I mean, with exceptions. So there are cases where it's easy to build one, and for instance, cases that admit a potential. If there is a potential, then you can write the Lyapunov function, and the Lyapunov function is the potential. Right? In the sense that if you have like something like x dot I equal to minus dv dxi, then you're done. Right? Yeah. How do you check if you can do this? When you check the second derivatives, right? Whether these two are equal, right? If these two are equal, then it means that there is a potential, and therefore you're done. If these two are not equal, then it means that there is no potential, but there could be a Lyapunov function. And for instance, predator-prey, Lotka-Volterra, so competition Lotka-Volterra, they are not in this class. There is no potential, but there is a Lyapunov function. Something that also complicates the pictures is that you don't have one Lyapunov function, you can have many. Right? And it's easy to show that if you take a Lyapunov function and you take any function of a Lyapunov function, and that function is monotonically increasing, then that is still a Lyapunov function. So if you have a Lyapunov function L, and you take e to the L, if this is a Lyapunov function, this is also a Lyapunov function. Okay? So the point is that you have infinitely many Lyapunov functions. Right? So there is, on one end, there is no way to build one. On the other end, there are many you can build. So in practice, if you are in front of a new problem, the point is, first, you don't know whether there is a Lyapunov function. Right? Second, if you guess that there is one, you try to go into like sort of special cases where you are sure that there is one, and you can sort of try to guess it, and then you check whether that Lyapunov function applies to the more general case. But there is no really a recipe I can give you to. Yeah. So it's really like guess and then check whether it is. Okay.
But I just think it's a good tool.
Yes, it's a very, yes. I mean, the point is that this is in lecture 8, 9, I don't remember. The one on limit cycles, we show that the last one, 9. I mean, what I show is that if you have a Lyapunov function, then you are sure that there are no limit cycles, right? That already means that you don't always have a Lyapunov function, right? If you have a limit cycles, then you don't have one. So you can try to find one forever, but you'll never gonna find one, right? Other questions?
For the paradox of pesticide, the paradox of egg
Yes.
only because of the dependence, I mean the death in the part of the predator due to the pesticide.
Yes.
So for any competition models, this always exists because there is one cause, there is one factor which causes death on both species.
Yeah, but I showed, yes. So we have the pest, let's say, I don't remember which notation I used. Yeah. I was calling P the predator or the pest? The pest.
Predator. The pest is N.
N, okay. So the NBP is like R N minus R N 1 minus NK minus gamma P N minus delta N, and here I have dP, which is minus dP plus eta gamma P N minus Q delta P, right? Your question is, isn't all of this trivial somehow? And this, and this because I have this term here, and therefore it's obvious that there is an effect on the predator, right? Well, not completely, in the sense that if you look at the solution for n, so can you write? I mean, can you tell me the solution because I don't recall them and I can calculate, but so if you look at n star, or we were introducing u and v. And this 1 minus
1 minus delta. Delta minus delta.
Right? No. Divided by
1 minus delta minus beta times 1 plus q delta over alpha.
Yes, alpha, which is the parameter. Okay. Yes, yeah. Well, I mean, the point is, let's say that q is equal to 0, right? That there is no effect on the predator, right? The point is that if q is equal to 0, you get u star, which is like 1 over gamma, and v star, which is 1 minus delta minus beta. Okay. So the point is, if you don't affect the predator, the prey is not affected, right? That's the paradox. Right? So let's say the case q equal to 0, so where you don't kill the predator, right? You don't kill the predator, you kill only the prey, then the population of the prey, which is the one you want to kill, is unaffected, and the population of the predator is affected. Okay? The point is that if by doing this you also kill some of the predator, that makes the situation even worse, because you increase the population of the prey. Okay? So if you want, there are two sides of the paradox. One is, if you only kill the pest you want to kill and leave unaffected the predator, then the population of what you want to kill is unaffected and the population of the predator goes down. If by doing that you also kill some of the predators, then you increase the population of the prey. Okay? That is the paradox. Okay? So it's non-trivial.
But it happens in real life or not?
Well, I think that there are cases where, I mean, this is known that can happen. And if you want it, I mean, it's known that if you have cultivation where you give a lot of pesticides, or you sort of completely destroy the biodiversity, you also typically makes the system less resilient to perturbation. So, in practice, then it's a more tight. I mean, it's a tight balance of what the pesticide does and what pest you have. I mean, this is like a sort of simplified setting again, but yes, it can happen. I mean, the point is that pesticides have also other bad consequences on other levels. So they kill also pollinators, so which effectively reduce the diversity of plants, which effectively reduce the nutrients in the soil, etc., etc. So there are all these secondary effects. But yes, so it's something that can happen. And there is also like a sort of opposite. Well, no, that's not. I mean, this is also interesting. Let's say for another reason, which is the fact that you see how the population of prey is controlled by predators, and somehow it gives you a hint of the importance of predators in controlling an ecosystem. Right? Because the population of the prey, it's really controlled by how well the predators are. Right? And this, for instance, has a lot of consequences on fishing, where you basically typically kill the predators because you eat big fishes, which are big predators in the oceans. So that has a sort of cascading effect on the whole ecosystem. Yes.
So we can view the pesticides as a second predator that I meant that
It's a
the
cool idea.
population is not
Well,
matching.
in some sense, yes, you can think of that as a predator that kills both the prey and the predators, right? Or as another predator that competes with the first predator, effectively. But it's something that is fundamentally different because it doesn't change population, as you're saying. So a pesticide is not something biotic, right? It's not something that reproduces. It's at a fixed level, right? But yes, in some sense, you can think of this as you have another population of something that is at a fixed level, doesn't change in response to how much predators and prey there are, right? But kills, yes, that could be. So you can think at this as something, well, I mean, this perhaps is related to the last exercise, but you could think at something like you have one prey here and one prey and one predator, so this fits on that, and then you have something else which fits on both, right? And somehow, if this does not respond to changes in population here, that will be exactly the question, right? And somehow, how you increase the population of this, or the attack rate, or you effectively increase this delta or this Q, affect the population of this. I mean, there is a lot of space to generalize this, but the important message is that the effects are, even in this very simple setting, which is something that is almost linear, right? It's just quadratic, this equation. You have these effects which are very counterintuitive with respect to what you think will happen based on linear response, right? On if I increase this is going to happen, right? And this is fundamentally different because if you increase this, then you decrease that, then you increase this, but then you has the opposite effect, right? And this is fundamentally because of nonlinearities. So this was the goal of showing you this example.
Can I ask a question about 7?
Yes.
There are no more questions.
Do we want to move in the magic world of epidemiology?
Right.
Yes. Regarding 7, there was a error, a typo that was spotted in the SIS model. I'll perhaps reshoot the video, but it should be under control. Yeah, there was not something major. Okay, question.
Okay. So, in which cases do we use the SIS model, and in which cases do we use the SIR model?
Well, okay, good question. So these are sort of two very specific cases which are sort of conceptual models. Then in practice, what people use is something more complicated, as I explained. But sort of this corresponds to two extreme cases. So the SIS model corresponds to the case where you don't have, for instance, any immunity to the disease. Okay? So basically, you get a disease, you are infected, then when you are not infected anymore, you are immediately susceptible. Okay?
So, like malaria, right?
Well, okay. Let me say how this happens. Yes.
This is for VIH and
Let me say yes. Let's go back to this. Then this is SIS model. SIR model is you get a disease, you are infected, you recover, and you are immune to the disease forever. Now, two comments. First and second. The second one relates to your point. The first one is, of course, this is a matter of time scales as well, right? So, in general, you could think for many diseases, you have some immunity, then decays over time. So you have diseases where you have immunity, which lasts for your life, and you're done. Like measles, you either get measles or you get vaccinated, you're done for your life. You're not going to get it again. Okay? Or chickenpox, or all the, I don't remember how they're called in English, but all these diseases you get when you are a child, And all diseases where we have this vaccine that most of us are vaccinated. Why are we vaccinated on most of us? Because there is a long-lasting immunity and it's easy to have an effective vaccine. Right? So those scenarios are the scenario where it's more SIR-like, and the others one are the other scenarios are where you don't have this long-lasting immunity, are more SIS scenarios. Now, there are very few diseases where you don't have any immunity, right? The fact that you recover typically means, actually, I think always means, that you develop some immune response and you're able to fight the disease. Right? The point is a question first of time scales. How long does this last? Right? So you can think, well, one, for instance, extension of this model is called the SIRS model, where you say, well, when you develop immunity, you are recovered, but then there is a characteristic time scales where you become again susceptible. Right? First thing. Second thing which relates to the question is, why do you become susceptible again? Right? There are two sort of related but different reasons. One is because basically there is a finite memory for some disease of your immune system. So your immune system forgets about the disease. This is, for instance, the case of the other coronavirus we are exposed to, the one of common cold. Or rhinovirus.
I think that COVID has immunity for.
Well, let's leave it on a side for a second. Yes. Let's talk. Yeah, let's talk about there are other coronaviruses. We are usually probably all of us have been infected by them, which are the ones that cause common cold, or rhinoviruses, which are the ones that also cause the common cold. When you have like the nose running, thanks. Those viruses, they have an immunity which lasts 2-3 years typically. These other coronaviruses. Okay, this is one point. The other point is that so there is a decay of our immunity. The other point which relates to malaria is the diversity of the virus. Right now, when we say, oh, you are immune to what, right? I mean, in principle, what we care about is, am I immune to influenza, right? Flu. Well, you are immune to that strain you got last year, right? But every year there is a release of a new strain because the virus evolves, right? For instance, flu is a fast evolving virus which escapes your immune system. So what your immune system does is that it recognizes sequences, right, on the surface, that are expressed by the virus, or the sequences that the virus used to attach to the. So it recognizes this virus. The virus, what does for a job is to try to escape your immune system. There are viruses which are very bad at escaping the immune system, like measles. It's a terrible virus. That virus is like sucks on that, but it's great at infecting others, right? That virus can spread over long distances, is airborne, etc., etc. There are other viruses that are they are perhaps less infective, but they are very good at evolving. They have fast mutation rate, like influenza, or they have a lot of recombination. So like malaria, which is not a virus, but malaria has this like repertoire of genes that are expressed, which are called VAR genes, and there is huge recombination between all of them. So the reason why you can get reinfected. Yeah, as a vector, yes. That's another part of how it spreads. But the genes that are recognized by the immune system, which are called VAR genes, they are on multiple copies on the genome, and they recombine very fast. So basically, the next time you get malaria, you get a different strain. That's why it's different. It's difficult to develop a vaccine, because you have a huge diversity of strains. For instance, common cold. Why do I get the common cold every 6 months if I'm immune to coronavirus for 3 years? Because there are many viruses, right? There is all the 3 or 4 strains of coronaviruses. There are all the strains of rhinovirus. So there is diversity in the pool of virus, and I'm immune to one strain but not the other, right? So there is also variation there, right? Which is here, it's sort of coarse-grained into I'm immune or not.
Follow-up question.
Yes.
So, some infectious diseases are caused by bacteria, others
Yes.
are caused by viruses. So
Yes.
do we use the same models for both, or are there different models?
It depends on what you want to model, right? So if you want to model epidemiology, so how a virus spreads in the population, what you care about is not that much the physiology of the disease agent. So whether the agent is a virus, whether it's a RNA virus, a DNA virus, a bacterium, a eukaryote, whatever it is, right? What you care about is how it spreads in a population and how the population responds to the spread in these categories here. Right, so that's what matters. It's always like when you are thinking of modeling this phenomena, it's always like you have to understand at what time scale you want to model these and what are the relevant phenomena you want to capture, right? And what are the relevant phenomena at that time scales that matter. For instance, do I want to model flu? Right? This is one of the best modeled diseases. It depends, right? On what time scale do you want to model flu? You want to model flu on the time scale of one seasonal flu, so starting from now through March, right? Perhaps you want to model that because you want to know how many hospital beds you have to allocate, how many people you expect to be absent for work, etc., etc. Then on that time scale, well, you can use an SIR model. I mean, with all the complications, but basically those are the relevant structure, right? Because this year, if I get flu in December, I will not get it in January again. I will get it December next year because it's another virus. So in this seasonal flu, I can use this. Right? Do I want to predict how to make the vaccine for next year? Well, if I want to do that, I have also to take into account the diversity of the virus, right? The fact that I have many different strains of flu and they are infecting different people, and at the end there will be one which is the emerging one. Okay, so it depends on the question you're asking, right? The reality is complex, it's complicated. You don't want to sort of write every single detail in your model. You want to capture some phenomena, and you want to understand what are the relevant phenomena at the scale you're interested in. Okay?
I have another question.
Yes.
It's about this declaration.
Yes.
Which model are they assuming in this?
I have no idea.
And
I don't think there is so many.
There should be an assumption, no?
Huh?
The way I think about it is that you should have a model first.
Yes, I
You
agree.
should assume, or you should explicitly state, or implicitly state that this is the model, and this is why we're recommending A, B, and C.
Yes, I totally agree.
This has like no structure.
I will not find it. Yes.
They didn't present any.
Huh?
They didn't present any.
They didn't present anything.
No, but I mean,
Oh, okay.
Yeah.
no, not that I am aware of. Right?
But which model should, so for policy making, which model is the best? There should
There
be
is no
only-
best model. I mean, I personally, I'm not involved in policy making, luckily, for the policy making, not for me. There is no, I'm not involved. But I know what kind of, and what everyone agree, every serious person agrees on is that there is no one model. So the best way to inform policy is to have several independent groups who develop independently models, and then you have an ensemble of models, and you try to see whether this model agrees on or not, right? Because there are different things that might matter or might not matter, and you want to know, you want to capture these sensitivity. Right?
So if we have multiple models, those are models, that is what we are suggesting will happen. How do you, when you, for example, we're in the middle of a pandemic right now.
Yes.
There must have been many models that were made for COVID-19.
Yes.
And they're being,
well, the way it works in practice is that, I mean, also depends on the country, but the way it works is that there is like typically an agency of the country that has a scientific committee, and this scientific committee like find like different groups that work on this and ask them to develop models. And there are different groups, and they develop their models and they submit their predictions. Right? And then there is a discussion in this panel to what policy decision take, and then this suggestion go to politics, and then it's a more complicated level, right? Because politics doesn't involve only science, right? It also involves like the fact that you have to communicate decision to the public and have the public
Should respond.
I mean, yeah, the public should respond, but also, I mean, it's more complicated, right? You have elections, you have all these things, right? So
That's not what I'm asking. What I'm
Yeah.
asking is that how do models evolve and how, and
Well, they
now
start-
that we look back on this flu, for example, and we have different models for which question we're asking.
well, different models put an emphasis on different things. The problem is, the problem in general of modeling, like of doing prediction and forecasting, is that you don't have access to all the parameters you will need to write the most complicated models, right? So you have to make assumptions, and you have to emphasize different factors. For instance, one important factor is how different age groups respond to a disease, right? And how different groups transmit the disease, right? It's very different if you have COVID and you are 3 years old, if you have COVID and you are 20 years old, if you have COVID and you are 60 years old, right? It's very different for the effects that they have on you. It's very different for the likelihood of transmitting it to people. It's very different for the number of contacts are 3 years old versus a 20 years old versus a 60-year-old and the type of contact they have, right? So all these things, which are like things you experience, at the end, they should, in a model, are a number, right? And you should say, oh, a kid has 3 times more probability to have a close contact with someone than a 60 years old, right? So all these numbers should be determined somehow, right? And there are people that try to determine this number with social experiment, etc. But at the end, you have big uncertainty on this. And when you have big uncertainty on the parameters, you can choose either to make an assumption on those parameters, or to say, well, ignore these and assume that everything is constant. And the point is that different models emphasize these factors. For instance, one thing that we have not included in these simplified models is stochasticity, right? I discussed it explicitly. We write differential equations, which, as it will be clear in a couple of lectures from now, is basically equivalent to assume that there is no stochasticity, right? We know that there is stochasticity, right? So we say that, like, when you put your jacket, there is a 2% probability that I have COVID right now and that I'm infectious, right? This is a probability. I mean, if this is a probabilistic thing, right? And the fact that there is this probability implies that there is a probability associated to that then you on the first row you get it, you on the second row you get it, you on the third row you get it, right? So there is all these probabilistic phenomena, right? To this, the fact that there is a probability and not a certainty matter, it depends on the phase, right? If something is in small numbers, probably it matters more. If it's something is more large numbers, all these things get averaged out. Right? So some models include that, other models don't include.
And herd immunity without vaccine. What about that?
What about that?
So I get that not everyone has to be vaccinated in order to achieve herd immunity.
Yes.
But in the case of COVID,
Yes.
can we achieve herd immunity without the vaccine?
Well, the point is, how do you achieve herd immunity?
That's my question. Exactly. I don't know how.
You achieve herd immunity by me removing the mask now and yelling and going to bars and taking COVID and give it to you. I mean, that's the way you achieve herd immunity. Right? So
if you don't do
That's what it is.
At least 50% of the population needs to have the COVID, right? To reach.
well, it depends on what is or not, right? If I go to bars to get
Yeah.
COVID, it's going to be even higher. So
I think that there is not so many people with COVID.
yes. So right now that we are in this phase where things are moving faster, I mean, we don't know the exact number, but I think not. I mean, probably the population that is currently having COVID in the whole country is about 2-3%, and probably if you sum to the people that have it, is less than 10%. So we are very far from herd immunity, and I mean the number of beds in ICUs are decreasing, etc., etc. So we see the effect of these even if we are at very low numbers. This is one problem of getting herd immunity, right? That it's a concept that is easy to say, but then there are, I mean, it's built over dead bodies, right? So,
yeah.
Right. First point. Second point, which is like, well, I mean, the disease is actually very dangerous for older people. It's less dangerous for younger people. Yeah, with all the caveats, yes. I agree. But even if it was, would that work? Well, I mean, the point is, let's assume that like you have a given R naught. This is like what was data exercises. Let's assume that you have a given R naught. And let's assume that you have 60% of the population and you have an SIR model. And you have 60% of the population who go out, party, etc. with that R naught. And then you have the disease spreading and then goes down. And you can perfectly isolate all the other 40%, which is impossible in practice. But let's say you can do it. And then you open the doors and all these 40% join the other ones while you have an R infinity of the 60% that had COVID. Right? Will the disease spread again or not? Do the math. Okay? The point is that, I mean, yes, you get, the point is that you have these 60% of the people and they are 40%, right? And you reach R infinity here, which corresponds to this R naught, right? But then this R infinity corresponds to a fraction of immune people at the beginning, which is X R infinity, right? So you don't have spread in the community if this number here is smaller, it's larger than 1 over R naught. 1 minus, yes, sorry. 1 minus 1 over R naught, right? Do the math. Right. Yes.
Can I ask about compartmental model?
Yes.
So, for this, for epidemiology, you use compartmental models because the population is 1. So you can also use compartmental models for competing population.
Very good question. There is yes. So very good question. You can do that. Actually, we are going to do that for the second part of the class. So in the second part of the class, when we are talking about evolution, we are mostly going to be talking about evolution within a constant population, which means you have individuals that compete for the same resource, and that sets the total population, and then basically some are a little bit better, some are a little bit worse, how the structure of the population change. Okay, so we fix the total population and we say that. Now, is this correct or not? I mean, is this okay or not? It depends. Right? It depends because it's not obvious that the total population is independent of the identity of the individuals that are there. So you are sort of assuming that when you have two subpopulations that compete for the same resources, independently of how many you have of the subpopulations, the total population is fixed, which is not necessarily the case. Some cases it is, in some cases it's not.
So
it's not clear my answer. I can read the front.
For example, these compartmental models for predator prey?
No. Well, no, because the total population is not fixed, right?
Yeah. So it only happens when the sum is fixed.
Well, I mean, yes. So you use the word compartmental models is typically used only in disease ecology because you think you have a population with a given fixed size, and then you have different subcategories, and you jump from one category to the other, right? While in predator-prey models, you don't have a predator becoming a prey or a prey becoming a predator. Right? So you don't jump between compartments. You have like something somewhat similar when you have population structure. So you can write models of, let's say, predators and prey, where predators belong to different categories and prey belong to different categories. For instance, you have juvenile and adults, right? So you have young lions and old lions, and you have young gazelles and old gazelles, right? And it's more likely that a young lion attack a young gazelle, an old lion attack a young gazelle because it's also easier to prey. It's harder to prey an older animal, right? So you have these attack rates which depends on the age of the individual or the category they're part of, right? Yes.
I have a question connected to that.
Yeah.
So I am convinced that we use the epidemiological the models for fixed populations in one kind of population. But I remember one time I saw some kind of SIRV.
Yeah, you can do. I mean, there is like you are just limited by your fantasy in how many models you can create.
Yeah,
So,
but the thing is, the SIR is talking about a certain species, and then the D is the compartment for virus.
Ah, okay.
Yeah, that's why.
Well, you can. I mean, yes. So you can. You don't have to think of this as too strict. So you can, in general, you can write equations for. And you don't need to have all these three summing to zero, right? So you can write explicitly a model with population where here you have a birth rate. Here, so you can say, oh, susceptible individuals. When you are born susceptible. So there is some birth rate, which is S plus I plus R, right? And then there is a death rate where you can die because you are susceptible. You can die perhaps with a different rate when you are infected, and also with another rate where you are recovered, okay? And so here you don't have a fixed population structure, and then you have all the usual terms, right? Beta, I, S, N, minus. Okay? And then you have here minus gamma I, and gamma I, and then you can say, well, this beta depends on the virus, which also, well, here reproduce when they have. Okay. We are actually at the end of the session, so at the end of all of this journey, we're going to study a little bit models of viruses, of phages, which are the viruses that attack bacteria, and sort of is something similar. In that case, you have the population dynamics of bacteria and viruses, and they are coupled. So you also model explicitly how many viruses you have, how many bacteria you have, and you model their joint population dynamics.
So it means that this is still an SIR model, but you are viewing also.
This is nomenclature, right? Yes. So yeah, you have like these three categories, but you have also an explicit demographic description of the population. You can. I mean, the point is this relevant or not, right? So, is it relevant that, for instance, in this pandemic, the total population size, the number of people is changing? No, probably not, right? It depends on the time scale, right? If I'm looking at a disease spreading in a population, it doesn't really matter. If I'm looking at the next 10 years, and this virus has a strong effect on death rate, well, probably yes. But at that point, it's just nomenclature, right? What you call what.
I have a question. And the homework, the graph, because I was thinking about take a photo and put it in the.
Okay.
Yeah, but it's possible Or is
yes,
necessary
I mean,
that-
you can do that, but I think it's,
is there-
sorry, I mean,
is it-
as a last resort, yes, you can do that. Yeah, I think it's better for,
No,
Yeah.
I think it's better in a computer, but I don't know if I would have time, so I will.
again, I think it's, well, I mean, there is no universal answer. It's okay, I mean, I will not scream or cry if you send me.
Okay.
But I think it's most, I mean, as long as it is understandable, it's, in general, it's better for you if you get used to doing plots on a computer. So in the ideal situation, it should take you less time to do plots on a computer than by pen and taking pictures.
I'm thinking that.
Right? So it's no, I mean, I went through this, so I know that at the beginning it's not like this, right? So, but it becomes, I mean, you become better and better at doing like these plots because you do them, right?
Yeah, it's better. Is that I think that I forgot GenoPlot. I don't know.
Yeah, I mean, you can use Python. I think Andrea. I know. It takes. I mean, it takes time.
I prefer GenoPlot.
Yes.
I mean, yeah, I don't. I think you can choose what you want in general. It's good for your future that you are like proficient in these kind of things, right?
Okay.
You are gonna have to do these many times, and yeah, it's better to start earlier to do it because you're gonna do it anyway, and it's not that you're gonna have more time later.
Okay.
But still, still I understand your point. So
Yeah.
I will not. It's okay. Good. Any other question? So, who watched 8 or 9?
I watched 8,
Okay.
but I didn't understand.
No. If you want to ask questions, it's okay. But just understand how we are synchronized, because I think, I mean, compared to my expectation, I'm going slow, but I think I'm going too fast. So, I mean, in the sense that I wanted to have done more things, but I think I'm increasing the lag between question. Yeah. Okay. Okay, I'll try to go slower perhaps this week. Because like sort of to plan ahead, we are about at the end of the ecology part, in the sense that now, I mean, we have covered like one very small fraction of what ecology is, but you have all the basic tools to model populations, interacting populations, right? So if you want to model a community or population interacting, you know what are the building blocks. So we're gonna cover like, I'm gonna, in one lecture, sort of tell you a few things about chaos, because it's the other sort of attractors we have not studied. We have not covered. I will tell you sort of general features, introductory things. Then we're going to do sort of the last part in ecology about stochasticity. So we're going to introduce stochasticity in the ecological context. Then I think I'm going to do another one on epidemiology with stochasticity. And then we are going to start with evolution. So with evolution, what we're going to do is to sort of zoom in and say, oh, okay, we have these populations now. Let's look within a population and to the fact that individuals are not perfectly equal, how this variation accumulates over time. Okay. And so we're going to focus on microevolution and the mathematical part of it, of course. So we're going to explore these, build up a lot of tools on stochastic processes, which should also parallel with the course of biophysics. So you should sort of see them from two sides, which is good. And then it's going to be January 2024. No, I'm joking. And then and then we are gonna, and then what I did last year is that in the last week we are gonna do something putting together ecology and evolution, in a model with virus and phages, which is also good because also puts a bit of epidemiology. So you see everything sort of coming together. Okay, this is more or less the plan. Then we'll see how the evolving situation evolves.
How many lectures will be total?
142. I'm joking.
No, I mean not just videos. Just lectures. We have 9 lectures yet. So.
I think we are a little bit less than half. So last year, when I have to check with last year, in the sense that what I did last year was to do 3. I mean, I was going faster because I was well for a different format, but I also ended up. I mean, I finished earlier than what I expect to finish this time. So I think I think 11, 12 more. We're not at half yet. Yeah. Don't look with like this lost.
Question.
Can I ask about bifurcation?
Yes.
Before you
Your question is after bifurcation, right? It's about something.
No, it's a general question.
Let's do bifurcation then.
Sorry. Before you said that there are only 3 kinds of bifurcations for one.
Yes.
So for all bifurcation, we can categorize that. This is a standard one to say that. Sorry. So if for example we find a bifurcation for 1D that it doesn't match any of the 3.
Well, I mean, okay, what bifurcation is that? I mean, you can. I mean, the point is, as I showed you, this classification comes from sort of expanding the equation close to the equilibrium and close to the fixed point, right? So if you have like you neglect many terms and you have weird combination of terms, you can have something else. But what is the bifurcation in mind?
The homework assignment.
The one with assignment.
But there are.
Well, there are 4 because there are 2 pitchforks.
Yeah. We have to do the transition or not?
The limiting cases.
I want to understand the question first because I don't understand. So, but is because of the exercise or something you have in mind?
Just a general question.
Yeah.
So, for example, maybe it looks like a saddle node, but I'm sorry, I didn't memorize
No, it's okay.
But for example, the saddle node goes from next one, to 1 and then 2, say 1.
So you go from, well, you go from 0 to 1 or 0 to 2? Huh?
No, my question.
Don't worry, it's okay. I mean,
For example, if the fixed point map is shifted, it's like a mirror view of one type. It's still that type.
it's like something like this.
Yeah. So if we get up.
This is pitchfork, right?
Yes. Sorry. No.
Yeah, it's okay. No, but or you're saying something like this. If you have something like this, well, I think that this. I don't know. I've never seen this, but. Huh? Something where this is unstable, but here it's not clear what you have. But if you have something unstable and then you have two stable like this, something like that.
So yeah, maybe if we have that, it doesn't look like the pitchfork.
Yes. Well, if it was something like this, that you have something unstable and then it becomes, well, a little bit weird. Let's say if it was something like this would be transcritical, right? Well, let's say you have to come up, let's do this. So write the equation you have in mind. You have in mind an equation or not?
I meant,
Or you are thinking, okay.
what?
So you are thinking whether it's possible to come up with an equation that has that feature.
So what if the bifurcations that I got doesn't match any of the
Any of the four?
core?
Yeah, but then I would ask you, what is the equation?
Okay.
Okay. I mean, if you write me, I'm happy to think about it. But it's hard for me to think whether you are in one of these very weird cases or you are in one of these cases but you didn't recognize. I mean, what you should do is to expand the equation around the bifurcation point and see what is the expansion around the bifurcation point look like.
I think that point is very complicated.
My question is about the book.
Yes.
So we've been using two books.
Yes.
And
Awesome. Yes.
yes. So what about epidemiology and evolution? Which books?
Epidemiology, I don't have any. Evolution, there are. I put them on Slack. I mean, if you go on Slack on paper and books or books and paper, you can find all the titles and also something more. Yes.
Okay,
No, go ahead.
okay. I have a question, but you have to see it because I don't know how to describe it. Because I don't know if from this graph I can see the stability of the models.
How? Okay. So when you have,
Yes, because I think that
let's say that you have like some f of x equal to ax minus bx, right?
yes.
And you have you plot b of x and you plot a of x.
Yes, but I want to know the stability of the points.
Yes. So what you do is that if a of x is larger than b of x, it means that f of x is larger than 0. So x dot is positive. So you grow. So in this region here,
Because
a of x is larger than b of x. So this is positive. So x dot is positive.
oh, okay. Right. Okay.
Any other question? Great. I can stop here. Good. So I'll hopefully see you next Monday. Otherwise, I'll see you next Monday on Zoom. Okay. And I mean, as always, let me know if you have any question.
Just one thing.
Yes.
For lecture 5, everything was okay. The sound was clear. It was okay. But for lecture 6, the sound is very
low.
Yeah.
I don't know. Because like sometimes I record with 2 different computers. So 5 was okay, 6 not okay. So I'll check which I did with 5 and which with 6, and then start with that. So was okay 5. 5 is the gold standard.
Okay.
Huh?
The 5 number.
Thank you. Yes, you got what is my point, my problem, like
Yeah, exactly.
3 minutes from now, which I have to say which.